Good morning, everyone. Thanks so much for joining. We'll get started in just a minute here. Give folks just a moment to keep on joining. Okay, it is 7:30, so I'm gonna go ahead and get started just to respect everyone's time. Thanks again, everyone, for joining this final webinar in our series we're calling the Gunnison Valley Energy Code and Building Efficiency for Builders. We're joined again today by Robby Schwarz, who has graciously been hosting all of these webinars, and we're going to be talking today about infiltration, ventilation, and manual J. If you go to the next slide, Robby. Thank you. Just a few intro items. My name is Dana. I work for the town of Crested Butte. I'm the sustainability coordinator, and these webinar series have been brought to you by what we're calling the Gunnison Valley Building Code Collaborative. Really, that is just a group of municipalities and jurisdictions that got together and submitted a grant to the Colorado Energy Office. We received an award through the Energy Code and Adoption and Enforcement Grant Program to host not only these webinars, but a scholarship program. And I'll talk about that in just a moment. So as I mentioned, this is the last webinar in a series of 3 that we recorded this spring. We do have all of those webinars recorded. I have been a little slow to get the last one out to you from last week, but we will send that out via email, probably in the same email that we send this one. So give me just a few more days to take care of that. And then all of the recordings will be posted on the sustainability webpage for the town of Crested Butte. So I want to highlight the scholarship program that also came out of this grant. It's a really great opportunity for contractors or builders in the Gunnison Valley or who serve the Gunnison Valley frequently to get some free money for energy efficiency trainings or equipment. This scholarship program funds up to $2,500 for really any training, certification, class that touches the energy code. So if you're not sure whether your classes apply, please reach out to us. The woman who is managing that program, her name is Crystal Lambert. Her email is at the bottom of that screen, or you can visit the Gunnison County website and search for the scholarship program. We really want to get this money out to folks, so please apply. Funding is only available while it lasts. So next slide, Robby. Thank you. And then one new program that actually is kicking off in June of this year is the Electrify and Save on Bill repayment program. And I'm talking to you all about this today because this affects contractors as well as residents or homeowners who are interested in implementing energy efficiency measures for their home. This is a program funded by the Colorado Clean Energy Fund. And folks can apply to this fund to basically pay the upfront cost of any energy efficiency measures. So that might mean new windows, that might mean solar on housing. And the payments actually get integrated into that person's utility bill over time. So as a contractor, this benefits you because folks can pay for these projects up front. And then it's nice for the homeowner because they're not paying that cost all at once. There is a caveat to this. As a contractor, you do have to get certified through this program to be on their approved vendor list through the Colorado Clean Energy Fund. that certification is free. However, you do have to go through a little bit of paperwork and an orientation. But if you're interested, please reach out to GCEA, our utility provider. And I should note that GCEA is the only utility partnering in this program right now. So it would be for homeowners in GCEA territory. But if you're interested, this is a really cool program that's just kicking off in this valley. So certainly reach out to the GCEA folks to learn more. So we'll go through really quickly just a couple of the Zoom hygiene items. If you have questions during this webinar, please feel free to include them in the Q&A box function. That button is at the bottom of your screen. We will address questions at the end, should there be any. Next slide, Robby. And if you are listening in Spanish and need the Spanish interpretation, you can access the interpretation using the button at the bottom of the screen. It should say English. If you click on that button and select Spanish, the Spanish interpretation feature should work for you. And with that, I'm going to let Robby take it away this morning. Thanks, Robby.
Welcome, and thanks so much for joining us again for the last of our three-part series. Today, we're going to be talking about infiltration versus ventilation versus the HVAC design manual J, or the heat load calculation that's happening in manual J there. So we're just going to dive right in and get going here. We'll talk a little bit about why we're going to have the conversation. We need to always talk about the building thermal envelope with regards to this. Air and how it works, and then ultimately infiltration, ventilation, and what else impacts the manual J, which is the heat load calculation for our HVAC design there. So when we begin this conversation, we have to have a clear understanding that our HVAC system simply will not work unless we have a sound building thermal envelope. And that's why the code really focuses on the building thermal envelope, having that continuous boundary condition between conditioned space and unconditioned space, which is mainly built from the alignment of our air control layer and our thermal control layer. But we also need to remember that we're talking about assemblies of things and kind of a belts and suspenders approach. And we went over that in our last trainings, how the code is really looking at the building thermal envelope there. So when we looking at the building thermal envelope, we obviously want a sound building thermal envelope to reduce the amount of energy that is going in and out of the building thermal envelope. We need to be able to depict it on our construction documents, and ultimately the quality of that building thermal envelope is dictating the amount of energy that we need to supplement in heating season and in cooling season to make that house actually comfortable. And that's what we get to when we look at the manual J process. So asking that question when we're looking at the construction of the building thermal envelope, is it there and does it work? We talked about kind of that focus on performance and the inspection process and the building process so that we can determine, is the insulation been installed, but has it actually been installed so it performs? Are the bath fans installed so they can actually perform? And we take that same concept to the HVAC when we're talking about duct systems or hydronic systems or heat pump systems. We can't just install something and assume it's going to perform. We need to do some level of inspection and testing and ensure that it's going to perform as intended. And that whole idea that we get what we inspect, not what we expect. Therefore, these kind of simple questions we can ask ourselves when we're walking around the house. Is the insulation there? Yeah, it's there, but we have to go a little bit deeper and say, has it been installed so that it actually performs the way that we are meaning it to perform? So we have the kind of this design process for how we build a house. We start with the design and pre-construction meetings, buying all the materials to build the house, actually constructing the building and commissioning the building, and whatnot. And then we have kind of a similar process for when we create an HVAC design for that house, and how we decide how we're going to heat and cool that house in the different seasons that we have here in Colorado and in the Gunnison Valley here. But what we need to understand is that this design process for the HVAC system that's going to be installed happens, before construction actually occurs. So we're making a number of assumptions about the quality of the building thermal envelope that this system is going to go into. And what I want to point out here is that, again, we need to do that level of inspection or that kind of quality control, because if these assumptions aren't actually carried out, if our house isn't as tight as we thought it was, if the insulation is compressed in the cavities and it's not performing at its rated R value, that's going to have a significant impact on the performance of the HVAC system that we're actually going to install in our house. So we begin the HVAC design process by looking at three real, fairly simple steps. It's software driven here. And the first thing that we're doing is we're calculating the heating and cooling load using the ACA Manual J. The code allows you to use something that's equivalent to ACA Manual J, but if you're using a manufacturer heat load calculation, for example, you're going to have to demonstrate its ability to produce results that are similar and or as accurate as Manual J. Then our next step is to select equipment that has the capacity to meet the loads that are determined by the Manual J calculation. So that's all wrapped up in the Manual S calculation there. And then lastly, when we're talking about duct systems, we need to design the duct system that ultimately delivers the heat via air to different rooms around the house. Now, it's not called Manual D, but there's a similar manual for hydronic systems. And I know hydronic systems are often more popular in mountain communities there. So it's kind of the pipe layout and the pressures that are in the pipe, and ensuring that we're getting each of the zones laid out properly so that we're able to deliver the heat through a hydronic system there. So ultimately, with the Manual J, we're looking at all of the building components there. And it goes back to the building thermal envelope. So clearly defining the building thermal envelope. And as the code says, the building thermal envelope creates that boundary condition that separates conditioned space from unconditioned space. So that Manual J is looking at all of these different components, and we're putting the square footage of those components, the R value of those components into the software. We're setting up different design conditions inside the house versus outside the house, meaning we're telling it what the temperature is, because we know that energy moves from higher concentrations to lower concentrations, and or from higher temperature to lower temperature there. And we're measuring, in essence, or calculating the BTUs per hour that move through each component of the building thermal envelope. And we're taking into account other features as well, like air leakage and infiltration and those things that we'll be talking about here. So our ultimate comfort strategy is to have similar temperatures from room to room and floor to floor. That's our goal in this design process. But the reality often is very different, because you can see the little picture of the house on the left here in the reality side of the slide. It's a thermal envelope that isn't very robust. In fact, maybe it's not insulated at all. And so the strategy to try to maintain 70 degrees temperature in there is just to dump a boatload of energy into that house. And the reality is that that's not a very efficient means of heating a home. So we've reacted to the expectations of the occupants of our houses, and we've changed the way that we build our houses. So we are insulating them. We're creating more airtight houses. We have better windows. We have better delivery systems as well. So we're able to deliver way less energy to that house and achieve the goals that we want to achieve, because we're relying on the building thermal envelope to be able to do its work and do its work well. And you can go even farther than, the code might require. The code is requiring a really good level of insulation and air tightness in the house, but there are programs out there like Energy Star for new homes, or Passive House, for example, that could take you further, and you could reduce the mechanical systems even further in those types of houses there. So when we start talking about infiltration versus ventilation, we have to understand what the terminology is. And so let's look at that in a little bit more depth. When we're talking about air leakage itself, that's when we bring in the terms infiltration and exfiltration. And basically, the definition is that it's unintentional or accidental movement of air into the building or out of the building. So infiltration is air that's moving into the building, and exfiltration is air that's moving out of the building. So with regards to air leakage and infiltration and exfiltration, there's no control, there's no predictability, it's unintentional and it's accidental. And so the way that we gain control and predictability of the airflow through our homes is to tighten up the building thermal envelope, to close off those holes, and we start gaining more control and predictability of the airflow in those houses. So the infiltration load is accounted for in our HVAC design through a specific input on the software there. And we use this device, a blower door, to be able to measure the infiltration of our houses there. So if you haven't done a blower door on a house that you've worked on, you should consider doing that. And I'll just throw out there, because we were talking about it before we jumped on here, there is a training that you could use your grant money on potentially in Grant County to teach people how to do blower door testing and duct testing in June here. So you can look for information on that as well. But ultimately, again, we are striving for control and predictability of the air leakage in that house, of this unpredictable and accidental movement of air. And in order to get that control and predictability, we simply need to tighten up the house. So if anybody asks you, are we building our houses too tight? We need to understand that the answer is always no. We want to build our houses as tight as we possibly can in order to gain more and more and more control and predictability. And then we need to ventilate our houses correctly, which is what we're going to talk about next year, because ventilation is one of the ways we gain that control and predictability. We put that air that's going in or out of our houses, or both at the same time. We know a specific rate. When you're talking about a specific rate, we're talking about the cubic feet of air per minute that is moving through that fan. And we know that the volume of that house is constant, and the volume is contained by the building thermal envelope. And if 1 cubic foot of air leaves the house, then 1 cubic foot of air has to come back into the house. So that's how we start gaining that control and predictability, by putting the fan at a specific CFM rate. We also are putting it on a schedule, so I know how long that fan is running, and in essence, how many cubic feet of air are leaving or coming back into that house, by putting it at a specific schedule and a specific cubic feet per minute rate there. So it's super important. Now, that schedule can be pretty simple, like running the fan 24 hours a day, or I can have more sophisticated controls that run the fan 8 hours a day, or 20 minutes every hour, which is roughly equivalent to 8 hours a day. We can do all kinds of things with these systems, but again, we're understanding more and more the control and predictability of the airflow that's going through the building thermal envelope from inside to outside across that boundary that's created by the building thermal envelope. And again, just like infiltration, ventilation loads are accounted for in the HVAC system. So when I always talk about building tight, we also have to always talk about ventilating the house correctly. And we have to have an understanding that ventilation is also an energy penalty, but it's an energy penalty that we want to take on because it gives us the ability to gain that control and predictability, but it also gives us the ability for background air or fresher air for the occupants, and also background moisture control in our homes as well. Now, there are some ventilation systems that are considered better than other ventilation systems because they can provide additional features like ensuring where we know exactly where the air is going in and out of, or being able to filter that air. Those types of things are things that only certain types of ventilation systems can provide us. And in your climate zones 7 and 8, you are required to use a HRV or an ERV, or what we call balanced ventilation, for your ventilation strategies in those climate zones. They're per the 2021 IECC. So you are getting kind of the best systems that are available because you know exactly where the air is coming from, the source of that air, and how it's entering and leaving the house. And you also have the ability to potentially add additional filtration depending on the type of ERV or HRV that you are installing in that house. So again, the two primary functions of ventilation is to provide fresh air from the occupants or for the occupants, and background moisture control. Now, fresh air is a bit subjective sometimes, especially maybe down here on the Front Range where we have a lot of red pollution days, or the wildfire season is starting up again in Canada, and we're starting to get some smoke coming down into the United States. Luckily, that smoke is more on the eastern coast right now, but those types of things can affect the ventilation systems and the quality of air inside of our homes. So these systems do have to have the ability to have an override button so that you can turn them off, so the occupants can turn them off. But we want to be clear that those buttons and those controls need to be labeled, and we need to educate our occupants so that they understand what those systems are for, and ideally they never override them permanently. Because it's crucial in our houses that we're building tighter and tighter, that we have more and more control, but those systems actually need to function and work and be running in order to get the better indoor air quality and ensure that these systems are functioning right there. So again, we're trying to figure out how to design these systems to gain better comfort, efficiency, and performance in our houses, and to ensure that our systems work and that our clients are happy in there. So we have to have that sound building thermal envelope. So we're just going to do a quick review of that envelope, being able to define it, and being able to depict it on our construction documents as required by the IECC. So again, the building thermal envelope is an assembly of things that are brought together to create this boundary condition between conditioned space and exempt unconditioned space. Now, you can think of it as as a primary air barrier on the outside, a thermal barrier on the in between, and then a primary air barrier on the inside of the house. And the code is trying to ensure that we have continuity of that thermal control layer and that air control layer all the way around the building thermal envelope there, and that we have continuity of that system, and that they're in alignment with each other all the way around the house there. So the IECC kind of defines the air barrier side in a little bit more depth. Again, it's an assembly of things, but it's really the continuity of that air barrier system within the building thermal envelope and its assembly. So again, it's an assembly of things. And then the code goes a little bit further and talks about, consciously talks about the continuous nature of that air barrier, how we need it all the way around the house. And again, why we are depicting it on the building thermal envelope is kind of dramatized by the green circles on this slide here where different components of our building assemblies come together. We're going to have to spend a little bit more attention on those areas there, because those are the key areas that are going to leak, where we're going to get infiltration and exfiltration through our houses. So the code is asking us to do this red line test where we put pen to paper. And as we draw that line that's defining that building thermal envelope around the structure here, wherever we have to lift our pen from paper is a quick indication that we're going to need to spend a little bit more time on that detail, that connection point where things are going to be leaky. And you'll find from the code that often it's focusing on the low side holes and the high side holes or connection points in our buildings, because um, we have this phenomena called stack effect, which is just describing what happens to air as it warms. As air warms, it rises, and as it hits the top level of our homes, it creates a slight positive pressure, and it's kind of seeking a hole to the outside. If it leaves, if it finds that hole and it moves through that hole to the outside, then we have a cubic foot of air that leaves the house, and we know then that another cubic foot of air has to come back into the house. So these air barrier systems, if we simplify it, again, we can call our interior drywall and our exterior sheathing our primary air barrier systems. Again, that doesn't negate the fact that a builder might say, my zip sheathing on the outside is my air barrier. Well, that's true, but the drywall is going to help as a belts and suspenders approach to help make that house even more airtight, to gain even more control and predictability. So from a code perspective, we are really kind of focusing on that belts and suspenders approach here. So someone might ask, what is house wrap then? Well, house wrap really is what we call a weather resistant barrier there. Now it can be installed to be a primary air barrier, to kind of take the place of our exterior sheathing as the primary air barrier on the outside of our houses. But generally speaking, we don't install it well enough to actually work as that. So we might call it more a supplemental air barrier, kind of in this assembly approach, another belt or another suspender to help make the house even more tight. But in reality, it is that drainage plane or the WRB or weather resistant barrier that we think of. And the function of these systems, these air barrier systems, the primary interior and exterior air barrier systems, is really trying to enclose insulations within cavities, because a lot of the insulation that we use is air permeable insulation, meaning that we want to be able to trap a pocket of stagnant air inside of that insulation in order to prevent the flow of heat through. It's the pocket of air that slows the energy or resists the flow of energy. That R value, R stands for resistance of the flow of energy from higher concentrations to lower concentrations. So we need to have that stagnant pocket of air. And when we're using fibrous or air permeable insulations, we need to enclose that insulation on all 6 sides of the cavities that are installed, whether those are vertical cavities or horizontal cavities. So you'll hear this out in the field. I need 6-sided enclosures. You need to add a top plate here or a bottom plate here, or attic side sheathing, or any of those things that we use to enclose cavities and close insulation. That gives us better air control, it gives us better thermal control, and ultimately it gives us better moisture control in our houses there. So air sealing and insulation is governed by the code. It says that we need to install it. The code does rely pretty heavily on manufactured instructions, and you're never going to read manufacturer's instructions and see that they say, install the insulation or the air barrier system kind of good, kind of okay. You don't have to install it perfectly. That's not how manufactured instructions work. So really, code compliance is it has to be installed almost perfectly. in accordance to the instructions. From a fiberglass bat perspective, it generally says in the manufactured instructions the bat needs to fill the cavity side to side, front to back, top to bottom, with no gaps, voids, or compressions. Now, that's very difficult to do with a bat and the insulation there, but the reality is that we need to strive to do the best that we can in accordance with the instructions. And then we have some additional requirements in the R402.4.1.1 air sealing and insulation table there that gives us some additional details of how to install these products. And we went through those in the last two presentations there. As a reminder, insulation works just like it works for this on this fleece jacket that we might wear on a cold winter day. So the objective of the fleece jacket, and the reality is it doesn't matter if it's a fleece jacket or a wool sweater or a cotton sweatshirt, the objective of the material is to trap a pocket of air. And as we trap that pocket of air, and if we can keep that pocket of air stagnant, we increase the resistance to the flow of energy. In this case, it's the resistance to the flow of energy from this person's body to the ambient outdoors outside of the fleece jacket here. But what we see is that if this person walks out on a windy day, for example, those pockets of air are moving in and out of that fleece jacket there. And so we don't have control of our thermal control layer here. And so we put on a nylon shell over the fleece jacket there in order to create an air barrier over the insulation. And that gives me that stagnant pocket of air. It stops the flow of air through that insulation, and it gives me a system that actually works there. So the same thing we are doing in our homes. We have insulation, and again, it doesn't matter if it's fiberglass or rock wool or cellulose or even spray foam. The objective of the insulation is to trap a pocket of air, and the resistance to the flow of energy happens by that air pocket, not the material. So the more dense the material is, the higher the R value, because its ability to trap that pocket of air. But so it resists conduction because it has that ability to trap the pocket of air, but often air permeable insulations don't have the ability to resist the flow of air through that material there. So we need to enclose that cavity with an air barrier system that helps define our building thermal envelope. And we have to do that in a continuous nature all the way around our house there. We are doing this often because and we have to help our trade partners understand why they're doing this, because there's a big myth out there that insulation can stop the movement of air, when in reality, only certain kinds of insulation can stop the movement of air. Spray foams, for example, installed at specific thicknesses are also an air barrier and potentially can be a vapor retarder as well. But remember, we generally install insulation in cavities. And where do things leak? Where do we get that infiltration and exfiltration? We get that at the connection points where the rim joist meets the foundation, or where the bottom plate meets the subfloor, or where the top plate meets the trusses or the rafters. Those places often aren't covered by the spray foam. So just because we're using spray foam doesn't necessarily mean we're going to get an airtight house there. So we want to ensure that we're inspecting and in getting what we inspect, not what we expect there. So we have different types of materials out there. We have air permeable insulations like the fiberglass and cellulose and blown fiberglass. And then we have impermeable insulations, which are more carbon intensive, but also rigid and dry hard, and generally foam type products like open and closed cell foam, spray foams, and foam board products as well. And then we have the insulation table here that's helping give us guidance for how to install the air barrier systems and the insulation systems that we are installing that go beyond the building, beyond the manufactured instructions. So we have the components listed on the left-hand side of the column, the air barrier criteria on the center of the column, and the installation criteria on the right side of the column. And I'll just point you to that general requirements first component there to just emphasize that these components are examples of areas that we need to look at, but it's not all inclusive of everything that we're going to see, but we're going to use these same principles that are called out in this table for anything that we see in the house. And you can see in the general requirements that all breaks or joints or holes in the building air barrier have to be sealed, whether they are called out specifically in the ceiling section or the rim joist section or the air barrier behind the tub section. Regardless of where we see it, we need to seal up any hole, joint, or break in the building thermal envelope. And then likewise on the insulation side, it specifically says that air permeable insulation shall not be used as an air sealing material. And we need to help our trade partners understand that, because sometimes you'll see just fiberglass pushed into a hole in the building thermal envelope. And the assumption is that I can't see through that hole, therefore nothing's moving through that hole. And the reality is that over time, that insulation is just going to turn black as air filters through it. And we need to get a true air barrier over that thermal barrier there. Okay, so moving on, we're going to talk a little bit about how air actually moves in our houses from an infiltration and ventilation perspective. So the big thing that we need to understand about air is that air can be equated to a freight train, because a freight train is carrying cargo, and it's carrying cargo from point A to point B, just like this train is carrying coal, for example. And air is a freight train because it also carries cargo. Its cargo are things like pollutants, it's energy, it's vapor or water in its vapor state there. And so we need to get control of the cargo, because unlike the freight train, air can move energy or moisture or pollutants around our house, and it can dump that load somewhere, but it has a difficult time picking that load up and then moving it again. So for example, if air is moving from inside the house to outside the house, it might be carrying water vapor and energy with it. As it gets into the cavity, it might release its load into the cavity and continue to move out of the house there, but it has a very difficult time picking that moisture and heat up out of the cavity and then moving it out of the cavity there. So we want to ensure that it doesn't get in the cavity in the first place there. So it goes back to that question, can a house be too tight? And I answered the question before, and hopefully everybody understands the reality here is that no, a house cannot be too tight, and that ultimately we are asking the wrong question there. So what question should we be asking? Well, can our houses be underventilated? And a resounding yes. Our houses are underventilated. We did a residential energy field study in the state of Colorado. I happened to do the field work for that study, and we found that over 50% of the houses were not getting ventilated properly, when in reality, probably close to 95% of the houses were meeting the air leakage requirements of the 2021 IECC or 2018 IECC. It hasn't really changed much there. So we are underventilating our houses, and we need to kind of understand and utilize this mantra of building science that says we need to build our houses tight and we need to ventilate it correctly or ventilate it right there. So build tight, ventilate right is a catchy phrase that hopefully we all will continue to remember there. And our ultimate goal here is to gain that control of the airflow through our houses, but not only control, but also predictability of that airflow. And I put McDonald's here because it doesn't matter if I go to McDonald's in Gunnison or Montrose or Denver or Paris, France, or Beijing, China, I know exactly what I'm going to get when I order a Big Mac in a McDonald's anywhere in the world. And I know what I'm going to feel like when I eat that Big Mac uh, there as well. So it's that level of control and predictability that we want with the airflow in our houses there. And so that's why I use that example here. So we need two things ultimately for air to move through our building thermal envelope. We need a hole and we need a pressure difference across that hole. And so I might ask you, which is easier for us to control? Can I control the pressures or the holes in my building more easily? And so ponder on that for a second, and then we'll move to our next slide, and I'll try to demonstrate to you that we have more ability to control the airflow in our houses by controlling the holes than we do the pressures. I can't, for example, stop air from warming and stop that air from rising and rising to the high side of my house and creating a positive pressure there and that air seeking a hole to the outside. But I can stop the hole. I can fill up that hole and keep that air inside my house. So it's much easier for me to control the holes than it is for me to control the pressures in that house. So if we take this balloon as an example of a home and the rubber membrane of that balloon as the building thermal envelope of our house, we see that when air doesn't move through the building thermal envelope, we have equal pressures on either side of that rubber membrane or either side of the building thermal envelope there. But if I untie that string there, uh, that balloon is going to flow and across the room there because I have introduced a hole and I've created unequal pressures. I have higher pressure outside the balloon that's going to push against my building thermal envelope, and I have lower pressures inside the balloon and it's going to push that air out of the balloon. So again, I need a pressure difference across a hole. So I need both a pressure and a hole in order for air to move in and out of our houses there. So we can equate a cubic foot of air to the size of about 4 basketballs. So if a basketball enters our house, a basketball has to leave our house. The house is defined by the volume of air. I'm sorry, the volume of air in the house is defined by the building thermal envelope that is enclosing that volume of air inside the house. So I can calculate the volume of air in that house, which often in maybe a 2,500 square foot house is close to 30 to 35,000 cubic feet of air. And if one basketball goes in the house, then one basketball has to leave the house. So we can equate those basketballs to a cubic foot of air to kind of keep it in our mind what we're talking about here. So air in equals air out. And so I can control the building thermal envelope better by building it tighter and tighter and reducing the number of holes in it, but I can't really control these forces that are on the house on a pretty constant basis here. So we have stack pressure, we have wind pressures, and we have mechanical pressures in our houses there. And let me just double check here real quick. Okay, so the first one we're going to talk about is wind-driven pressures here. And you can see I've drawn a line diagonally across the house. So on the windward side of the house, there we have a positive pressure, and the wind is actually going to blow air through holes in our building envelope there. And remember, if we look at a typical outlet box, that typical outlet box has about a net free area of 1 square inch of hole area if we don't seal that up. And so the code is asking us to actually seal that up. So if air bypasses my primary exterior air barrier, it has the ability to get through the interior primary air barrier because I put 1 square inch of hole every 6 to 8 feet around my building thermal envelope with these electrical outlet boxes there. So the code is telling us we need to seal those boxes up when they're installed within the building thermal envelope, because we have a positive pressure just when wind is blowing on the windward side, but we also have a negative pressure on the leeward side of the house, and air is being sucked out of our houses on the leeward side through those same holes in the building thermal envelope. And, I have absolutely no control of the wind blowing in my house, but I do have control over the holes in the building envelope there. The next one in the middle there is the stack effect. And the stack effect describes, again, what happens to air as it warms. Air rises as it warms, and it's carrying that load. It's carrying that heat up from the low side of the house to the high side of the house. If it leaves through the hole on the high side of the house, then that air has to be replaced by air coming back in. And generally, it comes back in on the low side of the house where I have a negative pressure there. And so, again, 1 cubic foot in, 1 cubic foot out, 1 cubic foot out, 1 cubic foot in. That's just the relationship that we know with air. So air in equals air out. And then in the right side picture here, we have mechanical systems. And mechanical systems can create positive and negative pressures across the entire building thermal envelope or in specific rooms. So for example, when I turn on the dryer in my house, I am exhausting air out of the house. I'm also heating that air and exhausting heated air out of the house. But that air is, somewhere in the range of 300 to 400 cubic feet of air that's leaving the house. 300 to 400 cubic feet of air has to come back in. So I'm creating a negative pressure inside the laundry room where that dryer is running. If I have a forced air ducted system and I have more supply side leaks than I have return side leaks, I might create a negative pressure in that house because I'm sorry, if I have more supply side leaks than return side leaks, I might create a positive pressure because I am pushing air into a room and I'm not able to get that same quantity of air back to the furnace on the return side there. So you might think of a primary suite where the owners of the house are sleeping, and that room has maybe 6 supplies in it, but it doesn't have a return, or the return is undersized. So I'm pressurizing that room because I'm not able to get the same quantity of air back to it. And then with bath fans and whatnot, we can also depressurize rooms and create negative pressures in houses or specific locations of houses there. So these are forces that are affecting the leakage in our homes that I don't really have control over. So I want to gain control. I want to tighten up the houses by controlling the holes in the houses. So to summarize, air is a fluid, just like water's a fluid. Air in equals air out, but I need a hole and a driving force across that hole. So the driving force is also called a pressure difference across that hole. If either are missing, then air won't move. So we know for a fact that air in equals air out. And so I can put a measuring device on a bath fan and measure the amount of air that's flowing from inside the house to outside the house. I know somewhere air's coming back in to that through that building thermal envelope there at that same quantity. So a cubic foot of air is about the size of 4 basketballs. So we can keep that in mind as well as kind of a reference point there. Okay, so we understand a little bit more about airflow. We understand a little bit more about infiltration and exfiltration, or air leakage. Let's talk a little bit about HVAC design here. So we begin with our Manual J. So Manual J, again, is trying to determine the heating and cooling loads in the heating season and in the summer cooling seasons there. And we used to do that in a kind of haphazard way and just broad assumptions. So this was a device that people created where you walked across the street from a house and you put this picture up, and you could tell if it was a 1-ton or a 4 or 5-ton house, if that house fit within the drawing here. Not very scientific, but the reality is that people would do that in a variety of different ways, these guesstimates, to be able to size the systems in our houses. And what we've learned over time is that oversized systems don't perform efficiently. They don't work. Their coils freeze up. Their airflow is off. All these things. So as we're gaining that control and predictability, we also want to gain control and predictability of the HVAC design, meaning that we want to right size the equipment that we're putting in that house. But as we right size the equipment, we have to always remember the linkage of the HVAC design to the building thermal envelope. So this is all an integrated system. It's all the synergy where all these parts are coming together to achieve something that they couldn't achieve on their own. Therefore, we have to take each part of the system very seriously and ensure that they're all getting carried out and carried out well. So a load calculation doesn't tell you what size HVAC system we need to install. What it does is it helps determine the capacity of that system that needs to be installed. So the load ultimately tells me how much heating and cooling energy I need for that particular house to keep that house comfortable during the worst case components of our yearly environment there. But it also helps us figure out how big of an HVAC system we need to install. So meaning that system has to have the capacity to meet the heating and cooling loads of that house over the course of that heating system there. So often the equipment's capacity is going to be a little bit bigger than the load, and we must have enough ultimate capacity to meet the load. Now, this becomes even more crucial when we start talking about heat pumps, and we're not going to go into depth with regards to heat pumps, but what we know with regards to an air source or a ground source, well, really with an air source heat pump, is that as the temperature goes down, the capacity of the system goes down as well. Therefore, sometimes we need to size it bigger in cold climates to be able to get the capacity at that lower temperature. And or we're going to pick systems specifically in our climate region throughout Colorado. We want to ensure that we're installing cold climate heat pumps in order to ensure that we're going to get a system that has the ability to have greater capacity at low temperatures there. And we need to right size them for our houses as well. But it is something that we need to think about a little bit more, because as we talked about earlier, if the building thermal envelope isn't working, the HVAC system isn't working. So we can have oversized or undersized systems because the building thermal envelope hasn't been carried out there. So in this case, I might have designed the HVAC system with the assumption that the bats that were going to be installed were R20 bats, but they're compressed pretty severely when they are installed in the building cavity. So I'm getting performance more like an average of R7 or 11 or something like that, which is going to significantly impact the ability of that forced air system, that heat pump, that hydronic boiler to actually meet the loads of the house there. So again, from a fundamental inspection question, we need to ask, is it there? And has it been installed so it actually works? And this is the picture that we showed in our last training, but the same principle basically is here, that we need to inspect our building thermal envelope and we need to ensure that it's going to perform and perform well. So when we're doing our manual J calculations, we use a software to do that. And the manual J kind of morphs the manual J, the S, and the D together, all to create this output, this report of what we need to do with the HVAC system in our house. So We need to look at some of these key things, especially if there are any code folks on, code officials on the call here today. Are some of the things that you want to look at and review on the Manual J to ensure that you're getting a proper Manual J, because you're going to see here in a minute that some of these numbers can be fudged and we're going to get the wrong calculation here. So we need to look at the indoor design temperatures. We need to look at the outdoor design temperatures. We need to look at the square footage of the house and the building thermal envelope components to make sure that we've done a proper takeoff of that house. We need to understand what R values and U values the envelope components are being entered with, and how they relate to what's being proposed in that system there. The number of occupants and the number of appliances can change the loads for that house as well. And then obviously we've been talking about infiltration and ventilation and the loads that are associated with that. So I'll show you where you can find that information. Orientation of the house can make a big difference on the loads, specifically and more importantly with the cooling loads than the heating loads of the house. And then duct or piping or other distribution systems location can impact things as well. So let's begin with number one here and talk about the interior design temperatures. So the interior design temperatures are actually defined by the IECC. The energy code here. It says that the maximum of 72 shall be used for heating season and a minimum of 75 for cooling season there. So when we look at our HVAC design, we'll get a design information report here, and we can see that the inside dry bulb temperature is 70 degrees and in the wintertime, and 75 degrees in the summertime conditions. So we see that they've entered the right temperatures here. And so ultimately what the Manual J heat load is trying to do is it's trying to determine what an indoor temperature is and what an outdoor temperature is over the course of the heating season, and pick that worst case condition to figure out how much supplemental energy has to be added to the house to keep that indoor temperature at 70 degrees or 75 degrees when the outdoor temperature is at its worst case scenario there. So we have to figure out how we're going to get that outdoor temperature. And ultimately, I think we talked a little bit about the notion of delta T, or temperature difference across the building thermal envelope. That is what's driving the heat flow. So if we have a big temperature difference across the building thermal envelope, energy is going to move from, again, higher concentrations to lower concentrations, or in essence from hot to cold, either in one direction or the other, depending on where the energy is in its highest concentration there. So the indoor design temperatures are defined and created by ASHRAE. ASHRAE is an organization that creates a number of standards. They created this comfort zone chart, which is basically an average temperature where people feel the most comfortable. And so we see that in the wintertime zone, it's in that 72 range, and in the summertime zone, it's in that 75 range. And that's ultimately where the code got those temperatures. Now, for the outdoor design temperatures, they're also governed by ASHRAE, but it's not defined specifically within the IECC as the indoor temperatures were. So these temperatures, the code jurisdiction is going to look at the specific climate location for that particular jurisdiction and determine what the outdoor design temperatures. But ultimately, the temperatures are created for the cooling season by saying that this temperature can't be exceeded by 1% of the hours during that time of a year there, which basically is saying that in this case, I'm going to jump down here. In this case, on the right-hand side, we see that the summertime design condition input in this Manual J is 91 degrees, which is saying that only 1% of the time during the year will the temperature exceed 91 degrees there. So we don't want to design for that 1% of time. We want to design for the average 99% of the time there. And that's why we're using that design temperature. Now in Gunnison and Gunnison County, they're really, it's really considered a heating dominated climate. And so I don't believe that the jurisdictions have called out a cooling design temperature that you should be using. But that changes when we get to the wintertime conditions here. And so the same kind of thing is happening here. It's basically saying that in the wintertime, we want to pick a temperature that isn't exceeded 99% of the time there. So the worst case scenario in Gunnison is -22. So we don't want to design for something that's colder than that, because it's only colder than that maybe 1% of the time during the course of the year. 99% of the time it's -22 or warmer there. So our worst case scenario would be -22. Now, the design conditions that were entered into this particular HVAC design, or Manual J, were based on Denver. So we see that -1 and 91. I believe it's gone up to 93 now in Denver there. But we see that, again, it's dependent on the climate location that you're located in, where you're going to get those design conditions here. And ultimately, again, we're trying to figure out the temperature difference, the delta T, between inside and outside. So if I have a 70-degree temperature minus, so it'd be 70, it's 22. I'm just trying to figure out the delta T in the wintertime in Gunnison, and it's 92 degrees, the delta T between inside the house and outside the house, if it were -22 degrees outside. That means that we have a huge imbalance between across the building thermal envelope, and we're going to have a large heat drive from inside the house to outside the house. And so again, it means that we have to have a really strong, robust building thermal envelope there to be able to resist that flow of energy from hot to cold, or that delta T of 92 degrees there. So these are things that we need to look at and ensure that they've been entered properly, because if they aren't entered properly, we can affect the design load. We can undersize or oversize our equipment. And remember, our goal is to ultimately properly size there. So a group called Ibicus, which is a building science consulting and research firm based out of Pittsburgh, did some studies here, and they basically saw that if people manipulated the data that was entered into a Manual J, they're going to affect the loads pretty directly. So outdoor design conditions were manipulated, and they saw ultimately that it changed the loads pretty dramatically. The heating load was changed 26%, sensible cooling by 39%, latent cooling by 113%, and total cooling by 51% here. So really, we want to look at the heating load and the total cooling there. You can see that if those design temperatures are manipulated and not entered properly, we're not going to get the right loads in our HVAC calculations. And we'll see how these things are impacted in other ways as well. So the next one I want to talk about is the square footage of the house. Doing a takeoff of a house and entering the results, the square footage of all our building components into a Manual J calculation is not necessarily a simple process. And every person is probably going to get slightly different results. And that's okay within reason. You know, if you're within 10 to 20% of each other there, then you're going to be okay. You're going to have a pretty sound Manual J heat load calculation. What we're really kind of guarding against is fat finger mistakes when we're typing it into the software, or just really fundamental mistakes and misunderstanding about what you're doing. So when we're looking at the area of the house, you see the square footage and the volume are the two big calculations that we want to kind of double check here. So if I have a house that's almost 3,500 square feet, I just want to do a quick calculation or review the architect's numbers uh, quickly to ensure that 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 house is roughly 3,500 square feet and it's not actually 6,000 square feet or smaller or bigger. And the same thing with the volume calculations. We want to make sure that. The other square foot information that we're looking at here are the components that are entered in. So each of these components, from walls to windows to doors, anything that's defining the building thermal envelope is defined separately in the manual J calculation here. So we need to understand the construction description here. We need to understand the square footage of area that's being entered into the software, and is that within reason or not there. So a quick double check. Again, we don't have to be exact. We just want to double check to understand that they're within reason here. And then we want to ultimately double check the R values and U values that they're installing in the components here. So for the walls here, they say for foundation walls, they're using an R19 drape insulation here. And then for the 2x6 walls, there it's framed 24 inches on center with an R23 there. So we go to the R values here, and we see that in the R values, it looks like it's installed properly, but in the U value, is it been installed properly or not? So it looks like the R19, there might be a question about if that's the correct U value or not. And then, but the R23, it looks like when we do the reciprocal of the R value, we get 0.043, and that's what was entered in the U value as well. So it should be okay there. So we might go back to the designer and say, well, I'm not sure that your R value for or U values for your foundation walls have been input correctly. Can you double check that? And they might come back and tell you, well, remember, U values are describing an assembly of things. So it's not just the R19 that's being looked at there. It's also the U value of concrete, which is pretty much there's no R value, there's no U value in concrete. So, but they might come back and tell you, well, it's taking into account the soil, it's taking into account, the whole assembly of things, whereas R value is only talking about the specific component that is being installed there. But again, you're not seeing the direct correlation. So it's worthwhile asking the question so that you're not getting something that is falsifying. Because unfortunately, sometimes contractors want to oversize the equipment rather than right-size the equipment because they're often under the false impression of the past, when it might have been true in the past in really leaky, inefficient homes, that you're going to get fewer callbacks. But in our more modern homes, if we're not right sizing the equipment, you're probably going to start getting callbacks there for oversized equipment and whatnot. So again, this type of manipulation of window data, of wall data, of R values and U values can result in total cooling load manipulations or changes up to 24%, and heating load manipulations up to 11% there. So again, just those changes, if somebody's trying to manipulate the software, can make a difference. So that's where you would look to double check those types of entries into the software there. Okay, the number of occupants can also impact our loads here. So we've seen cases where people have added occupants to the house, and the occupants are generally described as the number of bedrooms plus one, assuming that in the primary suite, we're going to have 2 occupants living in that suite. So that's how we would size a typical house. So if I have a 4-bedroom house, I would want to enter 5 people into that house. So the occupants plus 1, the number of bedrooms plus 1 equal the occupants in that house. So Manual J assigns 230 BTUs per hour per person in that house. So for a 5-bedroom house, that would be a total of 1,380 BTU hours that we need to take into account. Now, that would be taken into account more in the cooling season because we're going to need to be able to cool that 1,380 BTU hours. In the heating season, we're actually helping to heat our house in essence there. Not very much, but we are helping it. So it's taken into account differently in the cooling season and the heating season there. So we've seen a Manual J that, for example, entered 23 people into the house. So we see that jump from 1,300 to almost 3,900 BTUs in that house. That, I guess that was for 17 people here. But you can see that it is a subtle way of potentially manipulating the heating load or cooling load for that house there. And it's something that we want to guard against, and we want to just make sure there, because the result in this was adding an additional 1/4 ton of air conditioning to that particular house there. So the occupants, the assumption again in this case is that it's a 3-bedroom house. So it would be 920 BTUs. So if we look at the worksheets for our Manual J's, we can see that the occupants in this were added. I blew it up here a little bit so it's more easy to see. We've added 4 occupants at 230 BTU hours per occupant, and you can see the 920 over there in the total. And then you can see the appliances are also listed here at 2,600, and we'll get into the appliance here in a second here. But this way you can just double check that they're not kind of manipulating the Manual J and that things are moving forward correctly here. 4 occupants, 920 BTU hours are taken into account for this 3-bedroom house. Remember, number of bedrooms plus 1 equal the occupants. We use that calculation when we're also calculating the ventilation needs of the house as well. Okay, so we're going to move to appliances here. So appliances also are a load, and it's called out here specifically. Internal gains, here it's telling us 2,600 BTU hours are being associated to appliances. Now, appliances are somewhere around 1,500 to 1,600 BTU hours per appliance that you add. We're really trying to take into account big appliances like refrigerators, for example, that are running pretty constantly, expelling heat into the house there, and that load needs to be taken into account. So when you're in this case, they're probably taking into account 2 appliances. We want to make sure that that number isn't up in the range of 5,000 to 10,000 BTU hours. Then we know that they're just adding appliances to be able to kind of manipulate again the Manual J calculation here. Okay, so again, we're looking at the I guess the study didn't take that into account specifically there. So, but we'll see some other areas where the Manual J was manipulated in the study, and the results are showing the percentage of the change in the HVAC calculation there. So the next thing we want to look at is the infiltration and ventilation loads here. So what we know is that our houses have to be tested and that our houses can't leak more than 3 air changes at 50 pascals of pressure across the building thermal envelope there. So we know that infiltration is a measured load, and we can take that into account in our manual J. Ventilation is also calculated and put in there, but we also now in the 2021 we have to measure that load as well here. So the manual J gives us a couple different ways to look at infiltration. We have infiltration that is estimated, which gives this level of uncertainty, subjectivity, and inaccuracy in the calculation there that we're looking at. The way that Manual J looks at the infiltration of the house is primarily from the perspective of stack effect, and it's dependent on the size of the dwelling there. So bigger volume dwellings, bigger square footage dwelling, they're going to assign greater stack effect or greater infiltration in that house there. So again, the Manual J method incorporates this pretty subjective infiltration and exfiltration sources that are based on some assumptions like the number of recessed cans, the number of fireplaces, the air tightness of windows, all these types of things that are added into our houses there. And so we want to try to be ultimately more accurate. So in an effort to be a little bit more accurate, Manual J gives you the option of choosing a default setting that's based off of tight, semi-tight, average, loose, semi-loose, or loose building thermal envelopes. And if you look at tight, for example, it basically is saying that all structural panels, it should say corner, sorry for the typo there, cracks, joints, and penetrations are sealed by meticulous workmanship using a combination of air barrier films, taping, packing, and caulking, versus semi-tight that says that the envelope conditions are approximately between tight and average there. So really, from a code perspective, we should never see anything that's less than tight or semi-tight there, because the code is asking us to meticulously seal the building thermal envelope in that house. So if you see default settings, always look for tight or semi-tight, and then really question why they might be using average or semi-loose or loose in that calculation there. So when we look at the design information, we can see the method of infiltration is simplified, and they're using tight there, which is great. So again, it's kind of this meticulous workmanship that's in alignment with how we're supposed to work on the building thermal envelope in accordance with the energy code, air sealing, air barrier, and insulation installation table there. So that's where you would ultimately look for how infiltration is being attributed to this particular house. We can also look at the worksheet here, and we can get a little bit more infiltration information by looking at the worksheet here. So we see the infiltration of this house, and the BTU correlation here is at 3,392 BTU hours that have been added to this house. So we now have Manual J8, which is a newer version of the Manual J softwares there. And we can see that the infiltration load here is defined a little bit better there. So you probably also want to ensure that your contractors are using the most recent version of the Manual J softwares to be able to get a better calculation here. But we can see that the heating load is being measured in air changes per hour at 0.34, and the sensible and latent loads, which are basically the cooling loads that are associated with the moisture that's in the air, there are at 0.18 air changes per hour there. And we can see that the loads associated with them range from 10,000 to 2,100 BTU hours here. Now, the thing that is a little bit confusing about how infiltration is assessed in the Manual J software is that it's reported as an ACH, but the number indicates that it's a natural air changes or an NACH number versus an ACH number. So you see the 0.34 as an air change per hour. That is incredibly tight. It's meaning that it's less than 1 air change per hour. And the reality is that it's not being measured in air changes per hour there. So air change per hour is what the IECC and the IRC use to measure air leakage. Manual J actually uses natural air changes or NACH rather than air changes per hour or ACH here. So air changes per hour is the number of times the volume of air in a home exchanges with air from the outside every hour. So when we have a code requirement that it's at 3 air changes per hour, it means that the volume of air inside that house exchanges with air from the outside 3 times every hour. Now, for NACH, it's the number of times the volume of air is exchanged with air from the outside, but it's adjusted for the climate that that house is in, the height of the house above the grade outside, and the exposure of that building to wind outside there. So the number is getting adjusted here. So the ACA, the air change per hour calculation is described here, and the air change per hour natural calculation adds in this N factor number here to adjust the air change per hour number and make it a natural number, which again is adjusting for climate, height, and exposure of the building to wind there. So that's where the N factor comes in. So as an example here, if we have a 2-story house that's 2,500 square feet with 9-foot ceilings, we can determine the volume of that house, and we can calculate the volume of that house if we measure the airflow through that house there. And if we have a CFM 50 number, a cubic feet of air moving through our blower door fan at 50 pascals of pressure inside the house in relationship to outside the house, in this example, that was 1,000 cubic feet of air. If we do run it through the calculation, we get an air change rate of 2.67 air changes at 50 pascals of pressure. Now, when we convert that to a natural air change number, we get a 0.18 natural air changes. And how we convert that to a natural air change number is we have to go to the chart on the right here, and we have to get the conversion multiplier or divider here. I guess it's a division. It's in the numerator or denominator. I'm sorry. So in this case, it's in zone 2. It's normal shielding. There, it's a 2-story house, and we get a 14.8 number that we have to divide our air change number by, and that gives us the 0.18 number. So it's important to question that, because it's our frame of reference, I guess, is primarily with the air change per hour number, and we might assume that this house is incredibly tight, much tighter than passive house would require, for example, there, if we were only looking at it from the natural air change perspective there. Ventilation is triggered by the blower door test in our older codes. So if you're doing a blower door test and the house is achieving 5 air changes or less, you have to add whole house control mechanical ventilation. Now that changed in the 2021 IRC, where we now have to add whole house control mechanical ventilation regardless of the air leakage. So that kind of sound building science principle of building tight and ventilating right have been incorporated into the code to just require both in our houses to gain that control and predictability here. Mechanical ventilation can be provided with, has to be provided, and it has to have some type of gravity damper if you have a dedicated duct to the outside that will open and close when that duct is bringing air in to the house there. And then we're also allowed to use either a supply and exhaust or a combination or balanced ventilation system in our houses there. Um, if our systems are connected to the air handler, if we have a forced air system, we also have to have a ECM or electric commutating motor, more efficient motor on that HVAC system there as well. And then we have to remember that in climate zones 7 and 8, you don't have the ability to add a supply or exhaust system. You have to only use a balanced ventilation strategy using an ERV or an HRV. So, quick explanation of the different ventilation strategies. We have positive ventilation strategies that are generally powered fans that are pulling air from the outside and pushing it into the house, and therefore blowing that house up like a balloon, creating a positive pressure inside that house. Now, that type of strategy we would not want to use in maybe Houston, for example, because the air outside is significantly more moist than the air inside. We have greater relative humidity outside than inside, and therefore we would be pushing warm, moist air into the house and then potentially out of the house through holes in the building envelope. So remember, ventilation strategies give us greater control and predictability, but some ventilation strategies versus other ventilation strategies allow us to know exactly where the air's coming in and or going out. So this supply side ventilation, I know where the air's coming in, but I don't know where the air is going out. But I've gained control and predictability because I've set the CFM rate that fan is pushing, and I put it on a timer or a control to understand how often it's running and how much air in cubic feet per minute are coming through that fan. Now, exhaust ventilation is kind of the same. We just turn the fan around and we're exhausting air out of the house. Any air that leaves the house has to be replaced by air coming into the house. So again, it's a strategy that's kind of dependent on our location. And in our dry climates here in Colorado, these two strategies work pretty well. But in humid climates, we might not want these strategies there. But I, again, have greater control, but I don't know where the air's coming back in. I know where the air is leaving the house, but I don't know where the air is coming back in. So to gain the most control and predictability, I'm going to move to an equal pressure or a balanced pressure strategy with our ERVs or an HRVs here, where I know where the air is leaving the house. I know where the air is entering the house. I can do some type of exchange across that coil there, so I can keep some of the heat in the house in the winter season. I can potentially keep moisture in the house as well, because we tend to have more moisture inside our houses than outside our houses in climate zones 6, 7, and 8, and even in climate zone 5, and well, in Colorado in general, we do. So I might want to control that moisture flow as well, using an ERV over an HRV in our climate zones. So how does this relate to the manual J? So ventilation adds, in this case, it adds 7,300 BTU hours to the heating load and almost 1,700 BTU hours to the cooling load of our houses. And we would look in the heating summary, we would get this design information page of the reports, and we would look there. In this case, it's a central vent strategy. It's pushing 117 CFM of air, and it adds that much load to the house. So again, the ventilation is a required detail in our modern houses, but it is an energy penalty to our houses. So we can reduce the energy penalty by getting more efficient fans, which is required by the code, and we can reduce the energy penalty by using balanced ventilation strategies that have the ability to recapture some of the heat and moisture that's going through the fans with that air from inside to outside our houses here. And you can see on the cooling side, we also are pushing the same amount of air, but it has a different consequence on the load of the house here. So when we get into the actual worksheets, we can see here that we have our infiltration, room ventilation in our houses there, but the infiltration loads in this case are 3,392 CFM there. Oh, I guess I wanted to show you here the newer version of manual J8, which is the line 16 there. It says ventilation loads, vented CFM, and in this case, they didn't add a ventilation system, but it's just reported slightly different than the older versions of the manual J software. So I wanted to just show you that here. So, you know, it can make a big difference how we're going to ultimately describe the air leakage here. So tight, I wanted to give you some kind of frame of reference from tight to loose here. We could see that a tight house is in the range of 1 air change per hour. A loose house is in the range of 8 changes per hour. So if you do see these rules of thumb kind of what do you call them? The default entries entered into the software, you never want to see anything less than semi-tight because the code requires at least 3 air changes per hour. And we know that the state average is at 2.5 air changes per hour. And we're continuing to get our houses tighter and tighter and gain more control and predictability. So if you were using average loose or semi-loose in the calculation, you would be, you know, frankly, you're going to be manipulating the software and oversizing the equipment that's installed here. So with regards to infiltration and ventilation, that study that the Ibicus group was doing there, we see that they manipulated the ventilation rates in these houses, and we're getting load changes from 12% in the heating season and 7% in the cooling season. So you can see this is impacting the heating season loads more than the cooling seasons, whereas the other manipulations were really manipulating the cooling season loads more than the heating season loads. Orientation can also impact our loads pretty significantly here. So we want to see where the house is actually oriented. And if we're working with custom homes, we want to make sure that it's oriented properly for that specific house and that we're doing a house specific load. And I know that there aren't a lot of production homes being built in the Gunnison Valley, but when you do production housing, you often do a worst case calculation there. So you're going to need to do a calculation on every load, every orientation of that house, possible orientation that that house could be oriented in, and then pick the worst one or the highest loads for that particular home if you're only going to do a one design for that house. Now, better yet, it would be to require a site-specific design for every house, but that's really up to the jurisdiction there. But you can see in the northeast location versus the south orientation, the difference in the sensible loads and the difference in the heating and cooling loads aren't that different, but the sensible and latent loads are pretty different here. So that would give us, again, on the cooling side, a half-ton difference in the cooling loads. And so the equipment that we would have to install would need to be bigger there rather than being right-sized. If you're working with the Energy Star programs, like in the city of Crested Butte with the new DOE Zero Energy Ready Homes program, you're going to have to do this type of evaluation so that you can right size that equipment for that particular house there. Because the DOE Zero Energy Ready Homes program relies on the Energy Star program to figure out the heating loads of the house. Duct location can also impact the loads pretty dramatically. If our ducts are located inside the building envelope as depicted in the left-hand picture, or outside the building thermal envelope as depicted in the picture in the middle here, you're going to add load to that house because we only require R8 insulation on that duct, and that attic is going to be, in your case, could be at -22 in the wintertime, and R8 isn't nearly enough insulation to stop the heat flow out of that duct into that attic space. And then in the summertime, we like dark color roofing, and therefore the attic temperature is going to get up into the 160 range there. And if we're trying to cool that house using a forced air system, it's going to be an issue there. So duct location can be an issue there, and also duct tightness, how airtight the ducts are, can be an issue as well. And we can see that it can manipulate the loads by 13% or 17%, depending on the numbers that we actually put in to the software there. So this is just kind of the results of all the manipulations there. We can have a heating load that's 55% greater than it needed to be, and we could have a total cooling load that's almost 100% oversized by these manipulations. And remember, as HVAC contractors are adjusting to building more modern, airtight, better building thermal envelopes, they're coming from a situation where they often wanted oversized equipment because it reduced callbacks ultimately. But in our modern day houses, that oversized equipment is not only energy inefficient, but it's also causing problems with the actual functionality of the equipment, which is causing callbacks and problems for HVAC contractors. So ultimately, we want systems that are right-sized for that particular house. And here, these are kind of techniques for understanding how we're going to get that right-sized equipment there. Now, there's some other pathways for air to impact the loads of our houses that aren't taken into account as directly. Combustion air comes into our homes, and the combustion air in the picture in the left here is put into a container to try and ensure that when the furnace isn't running and utilizing that combustion air, that combustion air isn't going to just migrate and flow around the house. Makeup air guidelines for kitchen vents are also an issue there. We should be conditioning that air, and we should be conditioning that air separately than our HVAC systems. But if we're not, we really should be taking into account the amount of makeup air that we're bringing in for that kitchen hood, and understanding that that's creating an additional load for the house there as well. With regards to the combustion air on the left-hand side, the codes are trying to address that combustion air and the impact of that combustion air on our houses by saying in section R402.4.4, rooms containing fuel-burning appliances, that these combustion appliance air openings need to be located outside the building thermal envelope or enclosed in a room isolated from inside the building thermal envelope. So basically, these rooms need to be sealed off from the rest of the house as an airtight building, with an airtight building thermal envelope. Those doors to those rooms need to be fully gasketed, weather stripped, and insulated. The combustion air ducts need to be insulated properly. And there are some exceptions for fireplaces and whatnot, But if I have a forced air system, or I have a gas burning boiler, or a atmospherically vented water heater, for example, I have to bring in combustion air for those appliances. And therefore, I have to build an airtight, air sealed, insulated building thermal envelope around that mechanical room that separates the mechanical room from the conditioned space of the house there, so that that combustion air doesn't impact the comfort and efficiency of that house and or the loads of that house. And you can see that when that mechanical room is within the building thermal envelope, maybe the center of a basement or something like that, it's very, very difficult to separate it from the rest of the house there. So again, if you were going to do it, you'd want to make sure that you get your air barriers up first, and then you cut right size holes through the air barrier to take duct or piping or wiring or other things through the air barrier around the house there. But again, in essence, it's much easier to just design with sealed combustion appliances. And one potential avenue to that is moving to electrified appliances, so that we don't need that combustion air at all there. Okay, so we have gotten to the conclusion of our assignment today, is thinking about infiltration, ventilation, and HVAC loads through the manual J here. So we really need to understand that synergy between the building thermal envelope and the HVAC design. The basic definition of synergy are two or more things coming together to be able to achieve something that we couldn't achieve before or individually there. So the envelope and the HVAC design, or the envelope and the mechanical equipment together, right sized and executed well, are going to give us that well-performing house there. We can't do it separately there. We need to think about the different air streams, and that the air leakage, the infiltration, the exfiltration are uncontrolled, accidental air movement through our building envelope. Whereas ventilation is controlled and predictable airflow through the building envelope. Yes, we might not know exactly where the holes are, but we know that when we put it on a schedule and we use a fan to move that air, that we have greater control and predictability. Combustion air, we don't have as great a control over. Makeup air, we do have control over, but we need to consider whether we're going to use those in the HVAC design or not. The fundamental building science principle, air in equals air out equals air in, kind of regulates this, all of this air movement. And we understand that we are building tight and we're ventilating correctly in order to get that control and predictability of the airflow in our homes there. So thanks so much for taking part in our presentation today. If you have questions, happy to stick around and answer any questions or have a dialogue with you. But if you also are welcome to reach out to me. Here's my email address and phone number.
Great. Thank you so much, Robby. What an awesome conclusion to what has been a really great series for the spring. At this time, I'd like to open up the question and answer period. You are more than welcome to add your questions to the Q&A box. I haven't seen any questions come through during the webinar. If you'd like to raise your hand and speak your question, please feel welcome to do that as well. Just use the raise hand feature and I can take you off mute. So we'll just give folks a couple of minutes here, and if we don't see any questions, then we'll just end early. And again, thank you, Robby, for offering your contact information so folks can reach out directly with more technical questions. So.
Anticipation. Well, I'll take the opportunity, since there aren't any questions, to make a couple shameless plugs. One is for the BuildTANK Buildcast. It's a podcast that's centered around people that are applied building scientists. So it's a good listen. If anyone wants to listen on their favorite platform, you should take a listen on that. And then I'm just going to say one more time about the Grand County blower door and duct leakage training that's happening. I believe that you could use your education dollars to that. You can get certified to be a blower door and duct leakage technician for code compliance there. So we'll send out some information about that as well.
Great, thanks, Robby. Let's see, it looks like we have one question in the question box. Anonymous, but not sure if I heard correctly. Did you say an ERV might make more sense in this climate than an HRV? How is it determined which is best for a given project? I hear conflicting information on this.
Yeah, so the big thing that's happened over time is that we've learned that ERVs don't have to be installed only in the south and humid areas, that ERVs have the ability to move heat, but also moisture, and it's going to keep moisture at its higher content level, whichever side of the assembly the moisture's higher. And so in the south, where we have more relative humidity outside our houses than inside the houses, the ERV is designed to keep that moisture outside the house. But here in Colorado and in Gunnison County, you've got more moisture inside your house than outside your house. And you might want to keep that moisture inside your house for health, but for hardwood floors or for other reasons as well. So an ERV is going to keep the moisture, a percentage of that moisture inside the house, rather than it just exhausting that outside the house. So the big thing we've realized is that ERVs work in Colorado as well as HRVs. So it's kind of dependent on your desire to focus on energy versus energy and moisture, and/or ERVs don't do quite as well as HRVs in terms of keeping the energy inside of our houses. Now, HRVs are somewhere in the 65 to 85% efficient range at keeping energy in the house, extracting energy from the airstream that's leaving the house, in other words, where an ERV, I think, caps out at around 70 to 75% ability to keep that energy in the house. So they're a little bit less efficient, but they also have the ability to move moisture, which the HRV doesn't have.
Thanks, Robby. Not seeing any other questions come through the Q&A box. And I'm seeing some folks drop off with no raised hands. So maybe we'll give 1 to 2 more minutes for folks to quickly type their questions or raise their hand. Otherwise, I think we can go ahead and end early. Okay. Last call for any questions. All right. Well, Robby, we really appreciate you, and thank you to our wonderful interpreters for joining us today. And everyone have a great rest of your week. Thank you.
Take care.